Okay. So, last year in Algebra 2, when you graphed a parent function, you took a test on just quadratic, or you took a test on just absolute value, or you took a test on just exponential. But this year, on your first test, you're going to have 12 basic functions. And not necessarily you're going to graph all 12 of them, but you could be responsible for any 12 of them. So those of you who had me, you know, like when we got to quadratic, I said the points we're going to use are -2, 4, -1, 1, 0, 0, 1, 1, 2, 4. And when we got to exponential, we were going to use -2, 1/4, and -1, 1/2, and etc. And so you had one thing to do, so you could memorize one set of parent points for that test. So that's not going to happen here. Obviously, you're not going to want to come into this test memorizing 12 sets of parent points. So you want to be able to generate a set of parent points based on a parent. Okay? So, the things we're going to need to know is, what do our graphs tell us? We want to be able to construct the 12 basic functions, analyze the functions graphically, and why. As you continue to study mathematics, you will find that the 12 basic functions presented here will come up again and again. By knowing their basic properties, you will recognize them when you see them. All right, so the first one is the identity function. And notice what its equation is. F of x equals x. So it is called the identity function because if x is 1, y is 1. Whatever you put in comes out. If x is 7, y is 7. If x is -10, then y is -10. What is it graph? A line. What is the domain of a line? All real numbers. What is the range of the line? All real numbers. So, our brain says all real numbers. Our heads think all real numbers. But remember, what are we going to write on a blank when we're thinking and saying all real numbers? Negative infinity to positive infinity. Negative infinity to positive infinity. Okay? For both domain and range. Please remember, if you are writing interval notation, it has to go from left to right for domain and bottom to top for range. So you can never end in a negative infinity. You have to start with a negative infinity from the left or from the bottom, and you can never start with the positive infinity. So negative infinity has to always come first, and positive infinity has to always go last, okay? It cannot be any other way around, okay? All right, so because I have a general concept that parent is a line, and I know in my mind what a line looks like and that its domain is all real numbers, then if I don't have a restriction on my domain, the easiest parent points to pick are -2, -1, 0, 1, and 2 for your x's. So if I pick for my x's -2, -1, 0, 1, and 2, what are my y's going to be? -2, -1, 0, 1, and 2. All right, I'm going to graph it. And then if I was told to graph this by a parent and a transformation, what is this going to do to those parent points? Move them up 3. Move them up 3. Now, depending on who your teacher was, you may have done that differently. Those of you who belong to me, I told you to take your pencil, go to -2, -2, and then just count up 3 and put a dot. -1, -3, and count up 3 and put a dot. Okay? Some of your teachers may have had you plot the parent and then move them. And some of your teachers may have said, okay, up 3 just means you add 3 to all of those numbers. I do not care which way you do it as long as you understand the transformation and you can get the final graph on the paper, okay? So, that's the identity function. It's a line. Not a great big deal. Most of you probably wouldn't even graph the line using transformations. If I had to take my guess, you would plot the y-intercept of 3 and move a slope up 1 and over 1. And not a real big deal as long as you understand that it is linear. All right. So, the next one, the squaring function. First of all, notice what it says. The graph of this function is called a parabola and has a reflection property that makes it useful in making flashlights and satellite dishes. So maybe over the last week we've probably maybe had to use flashlights that we don't think twice about. But the reason those work the way they work is because of a parabolic function that was used in designing them, okay? We just use them. Many of us will never design them. Many of us, outside of math, will never talk about parabolas again. But those of you contemplating going into engineering, parabolics are going to be a big part of design, okay? If you have cable that just comes through the wire, you probably don't notice it. But if you have satellite, those satellite dishes, the way that signal comes in and it gets dispersed out is because of parabolic equations that are used to form that thing. All right, so what do we know the domain of this is? All real numbers. So our domain is -infinity to infinity, all real numbers. What is our range? Greater than or equal to 0. That's what we're going to say. That's what we're going to think. But what are we going to write? 0 to positive infinity. Should I have a bracket on the 0? Yes, because the 0 is included. Okay? Does this function have symmetry?
Yes.
Across what? The y-axis. So what did we learn those couple of days before we left? That when something has symmetry across the y-axis, it is known as an even function. It is known as an even function. Which means f of -x is equivalent to my original function. So -x times -x becomes positive x squared. Agreed? All right. So what I want you to understand is that f of x equals x squared is also, everything we know about it is going to apply to x to the 4th, x to the 6th, x to the 8th, etc. They're all going to look like this. They're all going to have symmetry about the y-axis. They're all going to be an even function. The only thing that's going to be different, as the power gets bigger, it gets skinnier. It gets skinnier. Okay? It gets skinnier. All right. So because I understand that that whole set of parents have a domain of all real numbers, which has no restriction on it, when I get ready to build parent points, is it very acceptable to use -2, -1, 0, 1, 2? And what happens when we square -2? 4. 1, 0, 1, and 4. So is that a guideline for getting that on my graph? And then what would this do to those points? Move them left 3. So everything would move left 3. Now, if I change it to x to 4th, do I change the bottom line? If it's x to the 4th, is it going to change the well, that's the 1. Is it going to change the y? What is negative 2 times negative 2 times negative 2 times negative 2? 16. 1, 0, 1, and which is why it becomes skinnier. Because instead of having a point here at negative 2, 4, I now have a net point at negative 2, 16. All right, so that's why it gets skinnier and skinnier. All right. The transformations are going to work the same, but each of these will have a different set of parent points. Okay? Well, with that said, you know when you take a test, you get just a little bitty graph, right? And that 16 is not going to fit on that little bitty graph real easily. So, is it okay to take this graph and scale this by 4s or 2s? Do you always have to scale by 1s? No. Can I scale this one by 1s and scale this one by 4s? Yes. They do not have to be scaled the same. But here's what you do have to do. Notice there's nothing here, so I assume that these are scaled by what? 1s. Also, it's obvious to see because they're scaling it by 1s. All right. If you're not going to scale your graph by 1s, you have to tell me how you're scaling it. And you may pick 2s and you may pick 4s, and that's fine as long as you tell me that yours is scaled by 2s and yours is scaled by 4s. If you do not change it, I am assuming that you intend the scale to be what? 1s. And if you want it to change, then change it. And you don't have to change both of them to the same thing. You do not have to change both of them to the same thing. Okay? So, that's our even function. Remember, what we know about x squared applies to x to the 4th, x to the 6th, x to the 8th, and it's just that that thing gets skinnier and skinnier. Remember, the symmetry across the y-axis makes it an even function. Also, the fact that it's 2, 4, 6, 8 helps a little bit too. Okay? All right. Everybody feeling okay about that? Okay. The cubing function. If you had to look at the picture, what would you say the domain is? All real numbers. What would you say the range is? All real numbers. And you're correct. Domain and range are both all real numbers. All right. Does it have symmetry across the x-axis?
Yes.
No. Does it have symmetry across the y-axis? No. If I flip it over the x and then over the y, or vice versa, x then y, would I have the same graph?
Yes.
Which means it has symmetry about the what? Origin. Symmetry about the origin. And is symmetry about the origin like a 180-degree reflection? Like rotation. If I turn this 180 degrees, would I end up with the same thing? Okay? So when it has symmetry about the origin, then it is called a what? Odd function. And remember, that means f of negative x would equal negative f of x, which means the opposite of the function. To be the opposite of the function, how many of its signs have to change? All of them. Every sign has to change to be the opposite of the function. So, that's your odd. Guess what I'm going to write down here? That's also going to apply to f of x equals x to the 5th, x to the 7th, etc. As long as it's that odd. So, because my domain is negative infinity to positive infinity, is it okay to let my x's be negative 2, negative 1, 0, 1, and 2? And what is negative 2 times negative 2 times negative 2? negative 8, negative 1, 0, 1, and 8, which is why this piece is down here instead of up there, okay? Instead of it being up there, you've got your negatives. So if I do x to the 5th, this would be a what? What's negative 2 5 times? 32. So it'd be negative 32 and positive 32, okay? So somewhere along the way, you were probably told it would be to your advantage to know about 1 through 20 squared, 1 through 10 cubed, and I would say you want to at least know 1 through 5 to like the 4th power and the 5th power, just so that you can easily split them off without having to sit and think about what is that times that times that times that times that. Okay? All right. This is a what kind of function? Increasing or decreasing? Increasing, because is the entire thing increasing? All right. This is not a local maximum or a local minimum. It's just a bend, and it's called a point of inflection, okay, because there's a curve there. But remember, that's not considered a local maximum. A local maximum would be if my graph looked like that. Would that be considered a local maximum? And would this be considered a local minimum? Okay? So that's just kind of a bend or a point of inflection. What would I do if this is what I asked you to graph on a test? Who would I build the parent points for? X to the 5th. I build the parent points for x to the 5th, which would just mean negative 32 and positive 32, but everything else would look the same. And then what would I do to those parent points? You better do something else to them too. Reflect them over the x-axis and then move them down 3. Reflect them over that x-axis and then move them down 3. So then it's going to become a what kind of function? Decreasing, because then from left to right would it be decreasing? Okay? All right. Everybody okay with that one? All right. Hopefully when I turn it, it's going to look better.
Wait, I have a question.
Uh-huh.
What if there were parentheses around the x on that? That's me.
Okay. So it depends. If it's like that, then technically it would flip over the y-axis. Okay? But if it's like this, it would honestly do nothing. And if I wanted it the other way, I would have to move the 5 to make it a left or right. I would have to move the 5 to the outside of the parenthesis. Okay? All right. This is not in the order I wanted in, so hang on. I want to go to square root next. Here's the one I want. Square root. Okay. Has a restriction on the domain and the range, agreed?
Yes.
So, what's my domain? Greater than or equal to 0. What is my range? Greater than or equal to 0. Now, carefully think about how you answer my question. Can I take the square root of negative 2? I can, and it's going to be I square root of 2. On an xy plane, can I graph the square root of negative 2? So if I want to graph this function, I have to put it on a real number xy plane, which means there is no place for the square root of negative 2. So is this one of those functions where I don't want my x to be negative 2, negative 1, 0, 1, and 2? Okay? I know even roots have restrictions on them, And so I need to think differently about my x values. So does it make sense to you that if I want to do square root, that these would be more appropriate numbers, if you can see them, to choose for my x's? Why? Because they're all what? Perfect squares. So what would y be? 0, 1, 2, 3, and 4. Okay? I could choose 0, 1, and 2. But then I'm going to plot 0, 1, and 1.41 or whatever. You know, it's not going to be something friendly to plot. Okay? There is another parent that has a pretty big restriction on its domain, and it's log, where this one can equal 0. Remember, log has to be greater than 0. Okay? So think of the parent, think of the restriction, and if there's not a restriction, what's the easiest thing to use? -2, -1, 0, 1, and 2. All right. Notice what it says down there. Interesting fact. Put any positive number in your calculator, take the square root, then take the square root again, and then again, and again, and again, and eventually you'll get what? 1. Okay? We're going to pause right here because I don't want to start the next conversation because I won't have time to finish it. But this is where we will pick up tomorrow. We're not done with this one yet.